Okay, here are some more error-bound questions. This question asks, find the error bound associated with the fourth degree for cosine. So I went ahead and came up with the Maclaurin polynomial for cosine of x, and we've already created this in a previous example, so we don't have to go through that again. So I know that the error associated with the fourth degree polynomial is going to be something less than or equal to the next term over. So I'm going to write the general formula for the next term in my Maclaurin polynomial. Okay, let's plug in all the pieces that I know. Okay, for cosine and sine, it's always easy. This will always be 1 because that is the biggest value the derivative of the sine or cosine can take on, because they will be derivatives of each other. This value of x right here is whatever x value that I'm really trying to calculate. So this is 0.1. This c, it is a Maclaurin, so we're centered at 0. Okay, and this is it. And if you type this in your calculator, so your error bound is this. So your exact error of using a fourth degree polynomial to approximate the cosine of 0.1 is something less than 8.33 times 10 to the negative 8. If you want to find the exact error, you would take the cosine of 0.1 and subtract it from the polynomial at 0.1, and you will see that's 1.33864 times 10 to the negative 9th. So this is always less than something that is your error bound. Okay. Let's get to a couple examples that are not sines and cosines. Okay, this time, find the error associated with the third degree Maclaurin for e to the negative 0.1. So again, let's think about the third degree polynomial. We've created this for e to the x before, so I'm just going to write it up here. So this is our third degree polynomial. Okay. And really, you don't have to come up with the polynomial if all you're doing is calculating the error. I know the error associated with the third degree polynomial is going to be something less than or equal to the next term over, which contains the fourth degree, the fourth derivative. So this is my general formula. Let's plug in all the pieces that we know. Okay, this piece right here, the x will be negative 0.1. That's the actual value of x that I want, because the function is e to the x. So I'm replacing x with negative 0.1. This is a Maclaurin, so my center is at 0. So I'm going to plug in negative 0.1 minus 0 to the fourth. The 4 factorial on the bottom is there. Okay, this piece right here. In order to figure out this value for any other function that's not sine or cosine, you actually have to calculate that derivative. The function that we're talking about in this function is e to the x, so the fourth derivative is pretty easy. It will also be e to the x. You need to maximize the value of the derivative between where you are centered at, which is 0, and the value of x that you are actually trying to find, which is negative 0.1. So you need to figure out what number in this interval will make this value the biggest value possible. It will always be one of these endpoints here. It's not going to be a number in the middle, and it's actually when x equals 0, or we call this our z value. So the maximum value of the derivative is really e to the 0, which is 1. So that's what I'm going to plug in here. And if you punch this out on your calculator, this should be 4.67 times 10 to the negative 6. So again, that's still a pretty small error from just using a third degree. Okay, next one. Estimate the error in approximating sine of 0.3. Again, we're going to use the sine function using a fifth degree, so I know the error comes from the error bound associated with the fifth degree is something less than or equal to the term that has the sixth derivative in it. So I'm going to start with the general formula. Okay, let's plug in all the pieces that I know. We're talking about a sine function, so this will be 1. X in this case is 0.3. It is, it does not tell you what it is centered at. Let's just say it's a Maclaurin, so let's make this 0. So that's my error bound. Punch it out in your calculator, give me scientific notation. This is your maximum error bound. Okay. Last one. Okay, same thing. Use a Taylor polynomial of the second degree to approximate cosine of 61 degrees and find the maximum error bound. Again, the error associated with the second degree is going to be something less than or equal to the piece that has a third derivative in it. Okay. I want 61 degrees is my x, and really, if you're approximating 61 degrees, you are really centered at 60, because if you center at 0, it's too far away to give a good approximation. So really, your C is 60 degrees. So 61 minus 60 is 1 degree. I'm going to change it to radians. So this really is pi over 180. We're talking about sines and cosines. This is always 1. And then I have 3 factorial. This is 8.86 times 10 to the negative 7. So even though you may not know what the exact error is, this is the biggest the error will be, which is a pretty small number to begin with. So you can say that the second degree polynomial approximates the cosine of 61 degrees with pretty good accuracy.